structures. And a structure is any collection of rigid bodies that are connected by joints that are in static equilibrium. If you have a collection of bodies that aren't in static equilibrium that are connected by joints, that's what one thing we talk about in dynamics, and that's called a linkage. So, in parentheses, a collection of rigid bodies connected by joints that's not in static equilibrium is called a linkage. Okay, so we're doing structures. It's very similar to linkages, but linkages are things that move. So examples of linkages are drive shafts in an engine connected to the pistons, and or the bones and joints in your body are a linkage. Structures are like the trusses that hold up bridges, the frames of buildings, those kind of things. Any kind of, when you see like stoplights on a big pole hanging out over the street with things connected to it to keep it from falling, that's a structure. And I do structures pretty differently than anyone else. And so I'm going to explain why, and we will talk a little bit about the approaches that are used more often in statics. I just want to sort of introduce the way that I'm talking about it. In statics textbooks and in a traditional approach to statics, to structures, structures are broken up into two categories. The first one is trusses. And the requirement for a truss is that every member is a two-fourths member. By the way, this is good stuff for quizzes, so pay attention to the stuff that I'm writing here. Anything where I'm like making numbered bullet points and stuff, that's good candidates for quizzes. So every member is a two-fourths member. Right, it's canceled. No, we'll just go to the next one that's scheduled on the syllabus. I think it's the 29th, maybe. Okay, so every member being a two-fourths member means that you can't apply forces in between the joints. Forces can only be applied at the joints, and members can't have weight, and you can't, so blah, blah, blah. There's all these things, and we'll talk more about that. And then the other category is frames. And the requirements for frames are no more than two members meet at any joint. And second, no external loads are applied at the joints. The benefits of this approach I'll call this the traditional approach. Is first, a lot of times you get a big reduction in the number of equations, the size of the system of equations you have to solve. So the size of the system of equations to solve is reduced. Well, I said benefits. There's really only that benefit, but I mean that's a significant thing to consider. You know, it can be faster to do these calculations by hand. There are two main drawbacks. The first one is that before you can solve a problem, you have to carefully classify it, and it's not always super easy, especially 6 months after the class, to be clear to yourself about which one of these categories you're talking about. So you need to classify the structure you're working on accurately in order to use the right technique. And you need to remember two different approaches. And I guess there is a third one, is that not all structures fit into either one of these two categories. So some structures aren't solvable with either of these two approaches. Okay, so we're going to spend most of our time, our approach is a single method that works for everything. So you don't have to worry about remembering these two different approaches and classifying problems and stuff like that. It works for every kind of structure, so there are no gaps in this. Works for any structure. The downside is that in a lot of problems, if you classify, especially with truss problems, if you classify the problem accurately and use the truss simplification, treating it like a truss goes faster than doing this, you know. So this is a slower way to do it by hand, especially compared to truss simplification. But in the defense of this method, these two approaches, like this truss simplification, people used to use this when engineers did hand calculations of gigantic trusses, estimated loads that were happening on bridges with tons and tons of members, and there was no easy way to use hand calculators or computers to do the calculations for you. I don't think anyone in here is ever going to be in a professional environment where you're doing hand calculations of big structures. If that's a part of your job, either you or someone else will be or is or has written software to do it. And so having a method that works faster by hand, where you can do calculations of lots of things by hand, just really isn't a useful skill anymore. So that's not as important as it used to be. With, you know, modern computers, calculators. And in fact, if you ever needed to do a, yes, question? Yes, and so that's the only reason I'm going to talk somewhat about trusses later on, is because they might come up in classes later on, because that's sort of the traditional way of doing it. I've never heard anyone say, like, you know, I mean, I talked to a lot of students after they graduate and stuff, and I've never talked to a student who was like, oh man, you know, like I took this class and we did trusses all the time and whatever, but it does come up every once in a while, so you should know what they're talking about. But it's not, to me, it's not practical information, and so I'm going to give you a way that's more useful for writing programs, more general. You only have to remember one thing instead of two things, and when to apply them. So yes, that's an important question, but I don't think you'll find it to be an issue. And we will talk about trusses a little bit. Even, you know, like with the truss simplification, the big simplification is for the trusses. If you can cut down, if you have to solve a system of equations by hand, then if you can cut your system of equations down from 20 equations to 12 equations, that makes a huge difference in how long it takes to solve a problem by substitution, how likely you are to solve it without making mistakes or whatever. But even with the calculators you have sitting in front of you right now, that distinction is gone, you know. So we're going to be at the forefront of the new statics. Okay, ready? Okay, not really you guys, because you're my 10th statics class, but mostly me. Okay. All right, so what's the goal with structures? So what does it mean to solve a structure? What's the goal? Okay, so let me just draw a so let's say we have a collection of members like this. And a roller over here. And there's a force of 10,000 newtons there, 5,000 newtons there. So what does it mean to, so there's a structure, what does it mean to solve it? It's solved when you know the external loads on each individual member. Okay, so right now, well, first we'll treat this whole thing as a rigid body, and we can calculate the reaction loads here and here. And once we do that, and that's all stuff that you already know how to do. Once we do that, we know all the external loads on the entire structure as a whole. But we've solved this structure once we can look at this member and calculate all the external loads acting on that, and look at this one and know all the external loads acting on that. So we want to be able to break it apart, know the external loads, and you can probably imagine the benefit of that is once you have the external loads on one of these members, you have information that you can use to figure out, am I worried about it breaking here? Am I worried about this one breaking, you know? And that goes into the stuff that we're going to do when you take deform. Okay, so I'm going to start with a simple one, and we'll just sort of think our way through it, knowing, it's not really, this topic of structures, there's no new physics that I'm going to tell you. It's just sort of a way of approaching these problems that works consistently. So first, we're just going to think our way through it. And then after I'm done with that, I'll give you a set of general steps that basically you're just going to have to do a bunch of problems and ingrain these steps. And then by that point, you'll go outside and see structures everywhere and go home and calculate the internal loads, the external loads. Okay, when you get to that point, you're really screwed. Okay, so here's the first example. So there's a pin joint on the left. Connected to a member like that. It's connected by a pin joint to a member over here. This looks a little crooked, but it's supposed to be equilateral. I'm going to fix it. Okay, and there's a pin joint connecting them here. And let's say that all these angles are 60 degrees, so it's an equilateral triangle. And all the lengths are 1 meter. And there's an external load applied this way of 500 newtons. And just so we can refer to these, I'm going to call the joint on the left A, the one connecting the members B, and the one on the right C. And then I'm going to call the member on the left member 1, and the member on the right member 2. And then I'm going to say that the mass of member 1 is equal to, what should we say, 10 kilograms. And that's also equal to the mass of member 2. As structures go, this is a pretty simple structure, right? But just to sort of bring out the point of like the gaps in that sort of traditional way of doing structures, this simple structure cannot be solved by either of the two traditional methods of solving structures. You could do this calculation if we ignored the weights, and the weight isn't going to make a big difference here. So, you know, that 500 Newton force is a lot bigger than the weights of, well, I guess 100 Newtons. So it'll make some difference, but not that much of a difference. But using the traditional methods, you'd have to ignore the weights. If you want to put the weights in, you're stuck. But our way will work fine for this. Okay, so what does it look like up at the, let's think of a side view at joint B. Can you picture what I'm trying to get at there? And we're going to assume that that 500 Newton force is applied right at that joint. Here it looks like that 500 Newton force is applied to member 2, the way I have it drawn here. But it doesn't change anything in this problem to think of that force as applied directly to the pin that connects those two. Okay. We're going to think of this as applied directly to the pin. And another thing that we're going to do, this is sort of a key thing in this approach, is we're going to think of we'll always choose one member at each joint to lump the joint into. Okay, it doesn't matter which one, although I'll give you, I'll give you the way that I do it. You just sort of need a consistent approach to which one. But so what I'm going to always do is, this is member 1 and this is member 2. I'm going to always say that of the members that are connected at a single joint, I'm going to assume the pin is part of the lower number of those, the lowest number of those members. Okay. So I'm going to say, okay, the pin, instead of treating it like its own thing, which it perfectly could be, you know, it could be its own member, but I'm going to just, when I do free body diagrams, I'm going to include that pin as part of my member one. Okay. And so with my approach, you know, the way I'm thinking about it, this 500 Newton force is applied to member one, even though here it looks like, the way I have it drawn here, it looks like it's applied to member two. Okay. It turns out if you had it applied to member two instead, it all comes out the same. But what you can't do is treat it like this 500 Newton force is applied to both of these two members. Then what you're really doing is treating it like this is a 1,000 Newton force and everything's off. Yes, you could. So I'll always lump the joint in with the lowest numbered member that's at the joint. So in a really complicated truss, if you have a really complicated structure, if you have a joint that connects members 15 and 12 and 9 and 40, the lowest numbered member that's connected to that joint is 9. So I would say the pin is part of member 9. Okay. Okay, well, if we're going to calculate the external forces on these members, we're going to have to isolate those individual members. So I'm just going to go through one by one. I'm going to first use Newton's laws for member 1. Then I'm going to use Newton's laws for member 2. We're going to have a bunch of variables, a system of equations, and as soon as you have as many equations as you have variables, you can solve it. So first, member 1. What loads are applied? Yep, there's a 500 Newton force here because I decided to treat that joint as if it's acting as if it's part of member 1. I'm just lumping those two together. What else? Yep, there's a pin joint connecting it to the ground. I'll call that the force. Since that's joint A, I'll call that reaction at A. There's the weight, and that's acting at the center. So 10 kilograms times 9.81, 98.1 newtons. And then there's one more. So if you go around the boundary looking for where the surroundings make contact with the boundary, there's one more contact that we haven't put in there yet. Yeah, there is the force that member 2 is applying to the pin, which is part of member 1. It's a pin joint, so that's an unknown force vector. And I'm going to call that the force on 1 by 2. And I'll write out rho, force, moment. Yeah, that's a great question. So the answer is no, we can't. Not yet. But when we isolate the other member, we're going to have a force on 2 by 1, which is negative F12. And so we'll end up with a system of 6 equations for 6 variables. Okay, so I'm going to choose the about point here. You can put it wherever you want. And I'll start out with the force RA. The row vector is 0, 0. The force vector is RAX, RAY. Cross product is 0. Then the weight force, that's 0.5 times cosine and sine of 60 degrees. So that's 0.25, 0.433. The weight force is 0, negative 98.1. And the cross product is negative 24.525. And then the force F12, the row vector is 0.5, 0.866. The force vector is F12X, F12Y. Cross product is 0.5 F12Y minus 0.866 F12X. And then the last one is the 500 Newton force. That has the same row vector, 0.5, 0.866. The force is 500, 0. And so you get negative 433. So the equations, Newton's second law says RAX, RAY plus 0, negative 98.1 plus F12X, F12Y plus 500, 0 equals 0, 0. And the moment equation says negative 24.525 minus 0.866 F12X plus 0.5 F12Y minus 433 is equal to 0. Okay, so we did all that for these three equations. And like you pointed out, we have 4 variables and 3 equations. We can't solve anything yet. I'm just going to write out these 3 equations. So our first one says, and I'm going to put them in the form that we're going to use for reduced row echelon form. So 1 RAX plus 1 F12X is equal to negative 500. Second equation says RAY plus F12Y is equal to positive 98.1. And the third equation says negative 0.866 F12X plus 0.5 F12Y is equal to 457 0.525. So we have 3 equations and 4 variables, and those variables are RA, X and Y components, and F12, X and Y components. Any questions about that? Okay, so now we'll isolate member 2. There's a weight force of 98.1 at the midpoint. It's connected to the ground by a pin joint, so I'll call this unknown force vector RC. Yes? This one is a pin joint. In the example I did before that, there was a roller, yeah. But for this one, they're connected by pins. By the way, if you had a third, if we were doing this problem where there was a third member like this, then we would need this to be a roller for it to be statically determined. But that's a pin there. Basically, it's like a 3-member structure with the ground being the third member. Okay, and then what's happening up here? This is the most complicated part. Always the most complicated are the joints where the 2 members are in contact. Well, the pin is part of member 1, so that 500 Newton force is not applied here. But this member does touch the pin, okay? And the pin is part of member 1. So there's a force on 2 by 1. If we called this variable the force on 2 by 1, we would have 8 variables in our system. We'd have the variables RA, X and Y components, F12, X and Y, F21, X and Y, and RC. And we wouldn't be able to solve it. But Newton's third law says that F21 is equal to negative F12. And so we're going to write this in terms of a variable we've already defined, and then we only have 6 variables in our system. Okay? So that's a key part of this. Moment. I'll put the about point down here for this member. So first, the force RC. Rho vector is 0. The force vector is RCX, RCY. 0 moment. Then the weight force. The rho vector is negative 0.25, positive 0.433, and the force vector is 0, negative 98.1. And that cross product is positive 24.525. And then the last one is negative F12. The rho vector is negative 0.5, positive 0.866. The force vector is negative F12x, negative F12y. Those negatives are because of Newton's third law. And then the cross product is 0.5 F12Y plus 0.866 F12X. So Newton's second law says RCX, RCY plus 0, negative 98.1 plus negative F12X, negative F12Y is equal to zeros. And the moment equation says 24.525 plus 0.866 F12X plus 0.5 F12Y is equal to 0. Yes? Yes, and I think the easiest way to make that make sense out of that for yourself is just to think, when we isolated member 1, we used the laws of statics to come up with a bunch of variable relationships that are true. Okay, they're true because we followed the rules of Newton's laws. And then separately, we came up with a bunch of relationships between variables that are true using Newton's laws for member 2. And if all of those are true, then they all have to be satisfied at once. Does that sort of make sense? Yeah. So yes, between members, you can change the about point. Question? Yes. Mm-hmm. Okay, so now we're going to come up with equations 4, 5, and 6. Equation 4 says, well, I'm going to put it in a different order. Negative F12X plus RCX is equal to 0. Oh, you better not close. I'm safe. Ah! That better come back, or I'm going to freak out. 4 says negative F12X plus RCX is equal to 0. Equation 5 says negative F12Y plus RCY is equal to positive 98.1. And equation 6 says 0.866 F12X plus 0.5 F12Y is equal to negative 24.525. Okay, so now we have 6 total equations. And what's our list of variables? We have the vector RA, we have the vector F12, and we have the vector RC. So 6 equations, 6 variables. We can solve it. One thing that's worth noticing about this is you can't really make a structure any simpler than this one. And that's already 6 equations and 6 variables. Every new member that goes into the structure adds 3 new equations if we're doing a 2D problem. And so if you have a structure made up of 10 members, which still isn't the biggest structure you see outside or whatever, that's a system of 30 equations for 30 variables. So it adds up pretty fast. And you can understand why people wouldn't, you know, you'd want to come up with an approach to doing structures like that if you had to do them by hand that didn't require that many equations. We like equations, though. We say the more the better. Okay, so 6. So our equations are the rows. So 1, 2, 3, 4, 5, 6. And our variables, I'll call them RAX, RAY, F12X, F12Y, RCX, RCY, and then the constants. Okay, so from equation 1, RAX's we have 1, F12X's we have 1, so 1 here, and then the constant is negative 500. And everything I leave blank is going to be 0. Equation 2, RAY's we have 1, F12Y's we have 1, and the constant is 98.1. So 1 there, positive 98.1 in the constant. Equation 3, F12X's, we have negative 0.866. F12Y's, we have positive 0.5. And the constant is 457.525. Then equation 4, F12X's, we have negative 1. RCX, we have positive 1. Constant is 0. Equation 5, F12Y's, we have negative 1. RCY's, we have positive 1. And the constant is 98.1. And then equation 6, F12X's, we have 0.866. F12Y, we have 0.5. And the constant is negative 24.525. Okay, so I hear people doing this. Let me know when you have answers. Okay, so now let's take the last step, and we have these values of these forces we defined. Let's put them back into the free body diagrams and show what the external loads are on each of those 2 members. Okay, so member 1, we had a downward force of 98.1. We had this force vector RA over here, and that's negative 221 point, I'm going to round a little, negative 221.7, negative 334.9. And then up at the top, we had 2 forces. We had the 500 Newton force, and then we had the force vector that said negative 278.3, 433. Okay. And I'm going to rewrite that because any force vectors that you have acting at the same location, you can just lump into a single vector. So down here we have negative 221.7, negative 334.9. We have the weight force of 98.1. And over here, to add up those vectors, we have this vector of 500, 0, added to this one. We get what's 500 minus 278.3? 221.7. So we got positive 221.7, positive 433. And that's all the external loads on that member. And then the other member, up at the top, we have negative F12. So I'm going to take the opposite of both of these two values for F12. So that's positive 278.3, negative 433. Then we have the downward force of 98.1. And then at C, we have negative 278.3 and 531.1. Basically, all of D-form is about taking numbers like this and figuring out for the cross-sectional shape that we have and the material we have, how concerned are we about this deforming, like having permanent deformation? How concerned are we about it breaking? Where are we concerned about it breaking? Yes? Yes. Yep. Yep. Deform is basically all an introduction to stress and strain. Yep. Here's like a first comment on the truss simplification. If we ignored the weights, we could use the truss simplification to do this. In that case, we would get exactly for the external loads on member 1, we'd get tension of 500 exactly along the axis of the beam. And for member 2, we'd get compression exactly along the axis. And actually that sort of suggests the what that truss simplification is based on. The way of calculating trusses that lets you cut out all these equations is based on the idea that these forces, if the only forces acting on these members are at the ends, and you're at static equilibrium, then all the forces have to be along the axis of the beam. And if you know that, you can imagine if you know the directions of those forces before you go into it, you can cut out a lot of the variables instead of talking about these as two-dimensional unknowns. They're all one-dimensional unknowns. That's what the truss simplification is based on, just sort of loosely. Oh, yeah, that's right. So let me give a general method for structures, and then I think we'll be done for today. Then the next time, the next class, which I guess is a week from today, I'll just do more examples. We'll spend a good bit of time doing this. So here's a general method for structures. So first, number all the members. And letter all the joints, just so you have something to refer to. And one thing that's going to be useful when you do this is, so let's say that we have a structure like this. This time, let's say we have a third member put in there. All of these are pin joints. So let's say we call this 1, 2, 3. It doesn't matter how you label them. And then A, B, C. One thing that's going to be useful a lot of times for figuring out what forces are acting on what is to do a side view of the joint. In this case, like if I was looking at this from the side, like from the right side, I would see member 1 here, member 2 here, and a pin connecting them. 1 would be diagonally away from me, 2 would be diagonally towards me. And then because I'm treating the pin as if it's part of member 1, I'm going to just connect those two like that. And then you can think of this as, you know, everything shaded is member 1, everything white is member 2. This approach will be really useful once we start getting more than 2 members connecting in a single joint. Yep.
When you mentioned, like, if it was a pin joint down at C, it'd be over constrained. Is that, if we have pins that are over constrained, does that basically mean pieces?
Yeah, that's a good way to think of it. Or not necessarily a whole member, but it means that you can put in a wimpier joint, a joint with less restrictions on it, or a member, and it'll still be at rest. So like if this was a pin joint, you know, we would be able to remove 1 degree of freedom, remove one restriction, 1 degree of like restriction from that pin joint, make it into a roller, and it would still stay static. And so that means that a pin joint we can't do it there. And also, by the way, in deform, what if that was a pin joint? It's not like anything crazy would happen. Like that's probably how you would build it. So it's sort of unsatisfying to think like we just can't calculate it if there's a pin joint there. Well, we can in this class, but if you take into account the deformations of the material, and there are ways to do calculations of things that are statically indeterminate. And so in deform, we'll talk about how to do that. Second, for each member, right, Newton's second law and rotational Newton's second law. There need to be free body diagrams for each of those anytime you use those. And be sure that you use Newton's third law to write your equations with the smallest number of variables. That's what I did when I represented F21 as negative F12 in the example problem. So for example, F31 is equal to negative F13. And so you'd replace F31 by negative F13 whenever it came up. One, two, four. And then the last step is write your system of equations as a augmented matrix. And use reduced row echelon form to solve. Any questions about the idea of this? Okay, so we're going to spend a ton of time getting practice over the next couple of weeks. Like I said, this is probably the biggest, the main topic in this class, so we'll make sure we spend a lot of time on it. Okay, have a good refresh and relax day on Tuesday. See you next week.